Well, this is somewhat of a continuation of what was in the last section. We're looking for solutions of differential equations by using power series about ordinary points. But in the last lesson, the couple examples we solved could have been solved by other methods. In this section, that isn't necessarily the case. We'll find some that can't be solved by other methods besides numerical, of course, or graphical. But we'll look at second order differential equations, but the method generalizes to higher orders. So suppose we have differential equation a2 is a function of x times y double prime plus a1 a function of x times y prime plus a3 a function of x. You know what? I forgot to say times y there, so bear with me. Times y equals 0 is, and that function is put in a standard form by dividing by the a2 of x, and then we have y double prime plus p of x plus y times y prime plus q of x, oh I forgot it here too, times y. There we go, equals 0. And some definitions. A function f is analytic at a point x sub 0 if it can be represented by a power series of x minus x0 with a positive radius of convergence. And what's called an ordinary point of a differential equation, if the point x0 is an ordinary point of this equation, here I am forgetting the y again, then that means that both p of x and q of x in this expression are analytic at x0, and analytic means can be represented by a power series. Alright, so what's called a singular point is one that's not an ordinary point. That means either p of x or q of x cannot be represented by a power series at x sub 0. Perhaps there's some problem with the radius of convergence of the power series, or perhaps division by 0 problem or something like that. So that what that forces to happen is there's no derivative at that point, and if there's no derivative, there's no Taylor series. So so if p of x and q of x in this are polynomials, sine of x, cosine x, or e to the x, then you know the differential equation is analytic at all points x0. But if p of x and q of x are products and sums of these functions, we're still analytic. But a quotient will cause problems. Then the differential equation is analytic except wherever the values of x0 make the denominator 0, because that's not allowed. There the derivative doesn't exist. Anyway, the points where the denominator of p of x or q of x is 0 are singular points, and also ln of x is singular at x equals 0, since derivatives as x equals 0 do not exist. So, that said, let's look into the existence of a power series solution. If x0 is an ordinary point of the differential equation in standard form, which I keep forgetting to put the y with, then we can always find two linearly independent solutions in the form of a power series centered at x0, which is kind of nice. So here's our solution, y equals this, right? But when we work this out, remember this is a second order equation, so we should only have two constants. The way I have this written, we have constant 0 times y1 of x, which is some part of this power series, and constant 0 and constant 1 times some function y2 of x, and y2 is also some portion of this power series. So the series solution converges for all x minus x0 less than r, where r is a distance from x0 to the nearest singularity, or the nearest singular point. So part of finding the solution may involve finding a recurrence relationship between the coefficients of the power series, some way that we can, say, factor out like a C0 from part of the series and a C1 from part of the other. You'll see that when we get to an example. So, okay, better look at an example now. What do you think?
You better solve that bad boy.
Okay, we will, but that'll be in the next video.